did an example 3A3. We use this example to introduce six-step approach to solve problems in this chapter. Let's do a quick review what we did. So a fire truck and has a ladder rotating and also extending. So we used 6 steps. The first 2 steps are to define where's your moving frame coordinate system and fixed coordinate system. So one should be on the ground, that's a fixed. Another one, the moving reference frame, the local coordinate system should be on the ladder, fixed on the ladder. So whenever you know where's your moving frame coordinate system, you want to draw a stick figure on that coordinate system. And step 2 is to label little xyz and capital xyz. Step 3 to find omega, which is the angular speed of your local coordinate system. And step 4 is to find alpha, which is angular acceleration of your local coordinate system. Once again, local coordinate system is your moving frame coordinate system. They're the same thing. And step 5 is to find what is the relative velocity and relative acceleration inside of your local coordinate system. And those velocity and acceleration should be in terms of little I and little j. And step 6 is to apply the equations we learned. In this chapter, we only learned 2 new equations. One is velocity equation, another one is acceleration equation. So step 6 is to apply those equations based on what this problem is asking for. Then you can find the answer. All right, that's what we did last time. Any questions on that example? No questions? Okay, I have a question for you. Let's go back to that figure. I want you to look at that position vector. Position vector R. What is position vector RP/O? So that should be the vector where which point should be the tail, which point should be the head. Yeah, if I write the vector like this, P/O, that means point O should be the tail. Point P should be the head of that vector. So if you draw that vector, it should look like this, right? That's R, P/O. Okay, if that's our vector, let's go that way. Can you write out vector RP/O instead of little I plus something little j? So I want you to write out little RP/O instead of capital I and capital J. So we have blanks here. First question is, are they the same? Should RP/O should the same value in this equation and this equation? Raise your hand if you think they all should have the same value. Raise your hand if you think they should have different values because they're in different coordinate systems. Yes, that's right. Notice here, little ij, big I, capital IJ, they're in different coordinate systems. Where's our big capital IJ? That's this guy and this guy. Where's our little ij? That's this guy. Do they have the same direction? No. But if they're overlapping with each other, the answer is yes. But in this case, there's an angle theta between them. So no. Okay, now your job is, can you write out what is RP/O in terms of little I and little j? So what is in front of I? The first equation. 1 and 2. So for the first equation, what is in front of I? Can someone tell me the value in front of I? B. What is the value in front of J, little j? 0. Okay. Let's all look at the first one. We have a question here. RP/O, just BI plus 0j. That's inside of our local coordinate system. It's pretty easy, right? Write out, just put B there, 0 in front of j. Okay, now let's look at this guy. Capital I, capital J. What is the value in front of capital I and capital J? Can somebody tell me? Yes. So B cosine theta. And what's in front of J? B sine theta. Double check here. Yep, that's the correct answer. So if you want to write out RP/O instead of the fixed coordinate system, you see that? It's totally different. Now it has both I and J components, and B cosine theta I plus B sine theta J. So that tells you what? In this chapter, we have two coordinate systems. Yeah, you have the choice. When you apply equations, you can either write out that vector instead of little I, little j, or big I, big J. That's your choice, right? You can pick either way. But for this case, I would pick the first one. Why? It's easier, right? Is it easier? Yeah, that it depends on the situation, but for this case, I think the first one is pretty easy. And I know often mistakes happens when you have sine and cosine. Mess that up. So that goes back to the equation in step 6. Whenever you apply equations, let's look at those quantities here. Here, if we have this term RP/O, you have the choice to write that as a big I, big J, or little I, little j. And also same thing for VP/O relative. We already mentioned that. You must write that as a local coordinate system, which is small I, small j, or little I, little j. If we have acceleration at AO, yes, you have the choice to write that as fixed coordinate system or the moving coordinate system. But at the end, if you want to combine all the I terms and J terms, you have to make sure you're working on the same set of I and J's. If you want, you can convert everything to little I, little j, or you have to convert everything into capital I, capital J. Okay, that's something you can easily make mistakes. Just want you to be aware of that. Okay, today we're gonna do another example as a practice. So we're gonna look at a very interesting example. This guy here. Example 3A2. It's a great example because this example contains the knowledge from chapter 1, 2, and 3. So it could give you a very good review about what we learned. So prepare you for our exam. Okay, let's look at this problem together. I don't know which page is that. Page 151 on your book. So in this problem, we know a disk, we know the radius r. Keyword here, rolling without slipping. Let me know if I pronounce that word wrong. It's not, I could sleep. So it's sleeping without sleeping on a horizontal surface. So which case is that? That's from chapter 2. We talk about two different cases, rolling without slip, or slipping. Which case is that? If you know the case, what condition you know, which is a special point. And we know the acceleration of the disk at the center O. We know the speed and acceleration. So VO and AO are given. We also know a particle P slides within a semicircular slot cut. Interesting. So there's a cut here, it's a semicircle, and the particle P can only move inside of this cut. And we know at that position, that particular moment right now, we're looking at particle P is moving with the speed of U relative to the disk. What does that mean? It says relative. Where we learn relative. Use instead of equation, do we have a term that's relative? Maybe that's relative. And we also know the rate of change of speed. Whoa, pay attention here. What is that? Rate of change of speed. When you see that, does that remind you something? Acceleration from what? Path coordinate system. If you see that whole phrase and couldn't think about anything about path coordinate system, you're in trouble, because that's kind of telling you, please make sure you consider this as a path coordinate system. Okay. Then we also know the radius of the slot, it's R. Okay, we want to determine the velocity of P. When P is on the perimeter of the disk, and it is immediately to the left of point O. We also want to find out what is the acceleration of P at the same position. So that's why I say this is a very interesting problem. Rate change of speed, that's from chapter 1, path coordinate system. The acceleration equation of path coordinate system has that term. That's V dot. And rolls without sleeping, that's chapter 2, right? And instead of this rigid body, we have a particle moving inside. So that's a moving reference frame. That's chapter 3, what we are learning. So this is a very cool example. But before we do this, I just want to clarify, sometimes it's confusing. Chapter 2 and chapter 3, the equations are very similar, but which equations to apply? So let's, before we solve this problem, use the 6-step approach. Let's just look at a look at this diagram here. First question is, how many rigid bodies do we have? Use your finger, show me how many rigid bodies in this problem. I want to see your fingers. Tell me 1, 2, 3, or 4, 5. Okay. Most of you think we have one rigid body. That's the disk, I guess. Now, what is P? Just a particle. Okay. Or if you think about that way, maybe that's okay. Maybe that's a tricky problem, tricky question. Yeah, particle P, we don't know its dimension, so it's kind of a particle. Okay, let's start over again. It's P and the disk on the same rigid body. No, let me repeat this. It's P and this disk belongs to the same rigid body. So I'm talking about that particle P and the disk. Can you consider them, these two, as the same rigid body? Okay. Let's maybe do this to clarify. What's the velocity equation we learned in chapter 2? V, if we use point P and point O. Can we do this? Vp equals Vo plus omega cross product Rp slash O. Can you use this equation? Can you use this equation for this problem we have here? I want you to take a minute to think about that. So like, we write another equation. Or can you use those two equations to this problem? The second one is the acceleration equation from chapter 2. All right. Now I want you to raise your hand if you think, yes, we can use those equations for this problem. Raise your hand if you think you can. Okay. Raise your hand if you think we cannot use those equations. Okay. The correct answer is you cannot use those equations for this problem. Okay. Yeah, you may have the question, why? And for those who raise their hand think you cannot use those equations for this problem, Hunter, what would you change? If you can change this problem, you can change this diagram. What would you change this in order to make sure we can use those equations for this problem?
Point B would be something on the circle, or a point on the edge of the circle, as opposed to an interact.
Yes. I'm not sure if you heard from Hunter. So if point P is fixed on that disk, on that circle, it's fixed there, it won't move inside of this disk. Then this is a chapter 2 problem. We can use these two equations. No problem, perfect. But now particle P can move inside of this track, inside of this disk. So it's not a chapter 2 problem anymore. For chapter 2, the equations we learned only applies 2 points that the position of these 2 points doesn't change. So that's the definition inside of rigid body. If you have 2 points inside of rigid body, the position of distance of these 2 points, they don't change because rigid body doesn't change its shape and size. So this 2 equation only applies to 2 points on the same rigid body. If you're not sure about this, make sure you write this down. This only applies to 2 points. Oh. What's going on here? Two. Won't allow me to write. It applies to 2 points on the same rigid body. So that's why those equations cannot be used for this problem. This is chapter 3, the new equations we learned. It's very similar to those equations, but it's different. So the chapter 3, the equations we learned in chapter 3 applies to the situation like this. So you have a rigid body, you have maybe a particle or something is moving relative to that rigid body. The equation can be used for that situation. Okay. So that's something I want to clarify because, and I saw some of you already making that mistakes. Right. Okay, now let's look at how do we solve this problem. Okay, I will erase this. This is just from chapter 2. Nope, it won't allow me to erase that. Okay. All right. Now let's look at the steps. How to solve this problem. First, find out what are the givens and where are we looking for. Givens, we have AO, VO, also know U and U dot. We want to find out VP and AP. Solution. Okay. Now I want you to apply the 6 steps for this problem. What's the first 2 steps? Step 1 and step 2. Look at what you did in the last example. Step 1, 2 is to find out where is your fixed coordinate system and where is the moving coordinate system. And draw that on the diagram. So where should I draw the fixed coordinate system for this problem? We should always choose where as our fixed coordinate system. The ground, yes. This is our capital Y and X. Okay, this problem is nice enough to give us the moving coordinate system, little x and little y. So we set up our y and the x right here at the center of this wheel. So remember, it's called moving reference coordinate system because it's moving with the rigid body. So it's not just fixed there. It's moving, it's rotating as this disc is rotating. Okay. Now we know step 1, step 2. Make sure you draw a little guy at your moving coordinate system. Okay. So like finish step 1, 2. So step 1, we want you moving coordinate system is our disk, and the fixed coordinate system is the ground. And for moving, we have X, Y, Z. For fixed, we have capital X and Y, Z. Now let's look at step 3. What is step 3? Step 3 is to find out what is omega of X, Y, Z. What is omega of that disk? Step 4 is to find out what is alpha of that disk. Let's don't jump steps. Let's finish step 3 first. Okay. I want you to look at this to think how to find omega. Can we find out omega? I'll call someone's name to tell me. Okay. Look, how to find omega? Yeah, omega of the disk. Here in this case, omega of the disk is the omega of our moving reference coordinate system. the little xyz. How to find that omega?
Using the radius of the disk, fastest velocity.
You should thank him. He told you this. Great. Yeah, that's one that method you can use. Use that equation there from chapter 2. You only look at that disk. You're not looking at particles. You know, if you only look at that disk, and we know one point, that's point O. We can also pick another point, special point, which is the instant center point. Let's call this one C. You can do that. Or like Cameron said, we can use the instant center method from chapter 2. Remember instant center method? There's the equation for omega. You don't remember, go check what we learned in instant center. There are 6 steps. In the last 2 steps, there are equations you can use. So from here, we can solve what is omega. Give a try. Can you apply that equation to solve what is omega? Let's call that point C. Okay. So this is how I would find omega. I will use the instant center method, which is easier. Omega equals speed of any point on the rigid body divided by the distance from that point, which in this case is point O, to the distance, to the point of IC, which is point C. So RO/C is the distance between O and C, which is R in this case. And remember, this disk is moving to the right. So it is clockwise rotation, as we defined. Clockwise is negative, so omega equals negative AO divided by R. Okay, that's how I find omega. You can also use the velocity equation. You will get the same thing. Now let's look at step 4. Find alpha of x, y, z. Okay. Krista, how to find alpha? Krista, do you know how to find it? Yeah, sorry. Alpha of x, a little x, y, z. Omega over radius.
No, it's sorry, it's the acceleration
Yes, that's actually that's the answer for that. But how do you find out that? Instant center. Okay, the instant center would tell us omega and speed, but it won't tell us anything about acceleration. So that's kind of the drawback of instant center method. You can find out omega speed easily, but it's hard to. We never learn anything about acceleration from instant center. Okay, so for acceleration, you kind of have to use that equation here. This equation from chapter 2 applies to this rigid body without looking at that particle P. So you can use point C and point O to analyze, to build an equation like this. And inside of that equation, we have alpha. Since we already solved omega, we know what is RO slash C. So, okay, try that again. Apply the equation from chapter 2 to solve alpha. So that's the equation from chapter 2. Applies for any 2 points on the same rigid body. Do we know anything about AO? What's the acceleration about point O, which is the center of that disk? What's the direction of that acceleration? To the right. So that only is applied, that only has the acceleration on X direction. So that is AOI plus 0J. That's on the left-hand side of the equation. So AC, what is AC? Acceleration at point C. Point C is our instant center for this disk. What's the acceleration for that instant center? That's the case number 1. Special case number 1. At instant center, 0 acceleration on I direction, but there is something on Y direction, on J. What is that? Is that omega R squared or R omega squared? Anybody remember? Look up your notes. Rolling without slipping. Case number 1. What is the acceleration at instance at that contact point? What? R omega square? Thank you. R omega square. Okay, that's our AC. And plus alpha, that's our variable we're looking for, unknown. Cross product RO slash C. What is that vector? RO slash C. Positive radius on J direction. And plus omega K plus omega K plus RJ. Okay. From here, this is what we learned in chapter 2. You can break this vector equation to 2 scalar equations and solve. And you can solve for alpha. Alpha equals negative AO divided by R. So step 3 and step 4 we require you to use the knowledge from chapter 2 to solve what is alpha, what is omega. Questions? Any questions? This will be on your exam. Just saying. So it would be a good time to ask questions.
Can we have just done omega dot and then that would have been b naught dot over the radius, which is a constant, which then is a naught over r.
Interesting. Yeah, never thought about that. Right. A acceleration, it's just angular acceleration should be just the omega dot. So if we already have the expression for omega, this guy, if we take a dot, omega dot can be negative VO dot over R. VO dot is AO. That's a new method to solve alpha. Thank you. Well, I think that applies for this case, but I'm not sure if that's always true. But this is the safe way to solve omega. Apply equations, do the cross product, break it down to scalar equation to find alpha. But that's a good question, Hunter. Never thought about that. Okay. Any other questions? No questions. We can jump to step 5. What is step 5? Step 5, we want to find out what is this guy, A, P, slash O, relative, and A, P, slash O, relative. So what is the relative velocity of that point P with respect to point O? So I told you on Wednesday, to answer the question as step 5, you need to put yourself in that figure, in that stick figure. Imagine you're the person who's standing at the center of that disc, and you're rolling with the disc. Then at one end of that disc, there's a particle that can move inside of that track. What is the velocity equation for that particle? Maybe another question. What's the shape of that track particle P is moving? It's a semicircle. From chapter 1, can we use any of the stuff we learned in chapter 1 to kind of express what's the velocity of particle P? Just want to remind you again. In this problem, we have a keyword here. Rate change of speed. That's kind of give you a hint. Let's use path coordinate system. What's the velocity equation for a particle inside of path coordinate system? What's the velocity? Mm-hmm.
ER plus v squared over rho P.
You're talking about acceleration. That's acceleration. Yes, that's right. Acceleration equals the speed dot, that's rate change of speed. In this case would be, it's given, it says, it's called U dot, that's called E, that's on ET, plus U over rho. Rho in this case is just R on EN U squared over R. So that's a path coordinate system acceleration. That's the equation we learned in chapter 1. So what is the velocity equation for a path coordinate system? just v et. V is the speed. In this case, it's u. It's given in this problem. Okay. Remember that? That's so. Like I said, everything's based on each other in this course. Even we're in chapter 3, we're still using stuff we learned in chapter 1. If you just totally throw your chapter 1 away, you're gonna have a hard time in second exam. Okay, now it's a little bit tricky here. Let's go back to the figure, look at where's that particle, where's that path coordinate system. So this is a particle. If we want to put ET and EN on that particle, remember what we did in chapter 1? ET should be on the direction of travel, right? And EN should perpendicular to that vector and pointing to the center of the curvature. Hey, this is our ETN. I want you to look at that ETN and our little x and little y. Did you find anything interesting? This is our y, x. Anything interesting about this too? They have the same direction. That means what? That means we can come back here, come back to these equations. You can just write this as u times I, write this guy as u dot I plus u squared over r j. Little I, little j. Boom. We have it. The relative velocity and acceleration for particle P with respect to O. Ooh. Finally, we're done with step 5. Let's move on to step 6, the last step. This problem, we want to find out VP and AP, so we need to use both equations. VP, the velocity equation in this chapter is VP equals VO plus VP slash O relative plus omega cross RP slash O. We know VO, we're given VO. But here's a choice. Do you want to write VO as a in the little xy or capital XY? That's your choice. Here, I think we'll just write VO inside of this fixed coordinate system plus 0j plus VP slash O relative, we already have that, which is UI, plus omega, we already have omega, plus RP slash O, that's a vector from point O pointing to point P. Should be just R, negative R on I direction. Yeah, right now, if you look at what we have, you will find out now we have big I, big J, and little i's. If you do this cross product, it will give you little j. So you realize we have mixed coordinate systems. If you want to do calculations, you want to convert them into the same coordinate system. But this problem is easy because little xy and the capital XY share the same direction. If you look at that figure, they share the same direction. So we can just simply replace off, convert them into either one. So if we convert them into little I and little j, then we end up with VO plus UI plus VOJ. That's the expression for VP. And that's how we find velocity vector for P. How to find AP? Do the same thing, apply that equation in chapter 3. AP equals AO plus AP slash O relative plus, oops, I bet that's wrong. Yep, that's right. The velocity, the acceleration equation is quite long. So make sure you, every time you apply this equation, double check your notes or textbook, make sure you have the correct equation. Okay, that's the long equation for acceleration. And you can plug in, substitute everything you know into this equation. I will skip the million steps to solve this and just give you the final answer. But in your exam and the homeworks, please do not skip steps. So AP, if you just convert all the coordinate systems into little I and little j, and combine all the terms, you will end up with A O plus U dot plus VO squared over R. That's our I component plus U squared over R plus AO minus 2VOU divided by R. That's on J direction. Okay, what do you think? It's a good review for all 3 chapters. Remember, once again, exam 2 is next Wednesday. Covers chapter 2 and 3, but chapter 1 is kind of there, you know. All right, that's all we have for today. I will see you guys next week, and have a good weekend.